Hello, class, and welcome to our review of Section 8.4 Improper Integrals. So I want to determine whether each improper integral converges or diverges and find the value of each that does indeed converge. So the integral from 3 to infinity of 1 over x plus 1 cubed in that denominator, dx. So applying this formula, this makes the limit as b approaches infinity of the integral from 3 to b of 1 over x plus 1 cubed dx. So applying that integration, this is the limit as b approaches infinity of, this will be negative 1 over 2 times x plus 1 squared, and this is evaluated from 3 to b. So, applying that fundamental theorem of calculus, this makes the limit as b approaches infinity of, this is negative 1 over 2 times b plus 1 squared minus negative, so plus, 1 over 2 times 3 plus 1 squared. And we want to apply this limit. So we could find that negative 1 over 2 times b plus 1 squared through just popping in values like 10, 100, 1,000, and that would certainly tell it to us. But I'm going to graph it just so we can see that visualization aspect of it, so we can see what this does indeed make for this graph. So for this is what the graph looks like. And if we increase this without bounds, though, looking on the right side of this graph, right, we could see when I start increasing the value of what b would be, we are starting to get values that get closer and closer and closer to 0. Here I am above 10, and you can see it's already negative 0.00259 at almost 13. And if I continue doing this without bound, we are getting very smaller and smaller and smaller and smaller, approaching that value of 0, as a matter of fact, which just means that limit, when we apply it to the negative 1 over 2 times b plus 1 squared, this approaches 0, which means this just makes 0 plus 1 over 2 times 3 plus 1 squared. That is going to make 1/32. So this makes 1/32 as that limit, which does mean that this does indeed converge. A second one I have, the integral from negative infinity to negative 4 of 3 divided by x to the 4th dx. So applying this limit from the formula, this would be as a approaches negative infinity of the integral from a to negative 4 of 3 over x to the 4th dx. So using that integration, this is the limit as a approaches negative infinity of, this would be negative 1 over x cubed, and this is evaluated from a to negative 4. So, applying that fundamental theorem of calculus, this is the limit as a approaches negative infinity of, this is going to be negative 1 over negative 4 cubed minus negative, so plus, 1 over a cubed. So that 1 over a cubed, again, we could pop in numbers for this as we want to approach negative infinity. So using smaller and smaller and smaller values of a, or I'm going to graph it again. So if we were to do the smaller numbers, that'd be like negative 10, negative 100, negative 1,000, negative 1 million if you want to. Or again, I'm just going to graph this one. Let me switch this over. So this is what the graph looks like. But since we're decreasing the value of a without bound, I'm going to look on the left side of this one. So decreasing this without bound, we could see that the value of a, I'm on the right one, gets smaller and smaller and smaller, right? At around negative 10, that was about 0.00101. And as we continue going down, this value gets smaller and smaller and smaller until this stops even approximating it. But we start approaching that value of 0. So this limit, as we decrease without bound, approaches 0. So this particular one is going to make 1 over, so we have that negative 4 cubed, that makes negative 64. With that negative in front, this would be positive 1/64 plus 0. So again, 1 over 64. And since this does make an actual answer, this one converges. And for this last one, I have the integral from negative infinity to infinity of x over x squared plus 1 dx. So ideally, we want to choose an arbitrary value. I'm going to use 0 for this one. And split these into two improper integrals. This would be negative infinity to 0 of x over x squared plus 1 dx plus, this is the integral from 0 to infinity over x squared plus 1 dx. So let's start with the leftmost one here. The integral from negative infinity to 0 of x over x squared plus 1 dx. Applying the definition, this is the limit, as this would be a approaches negative infinity of the integral from a to 0 of x over x squared plus 1 dx. So using a substitution, right, we could actually find this integral to be, well, let me first write the limit as a approaches negative infinity. Using a substitution, we could find this particular integral here to be, this will be 1/2 times the natural log of the absolute value of x squared plus 1, evaluated from a to 0. So because of that x squared in there, technically, the absolute value bars aren't really needed, per se. This makes 1/2 times the, excuse me, I need to write out the limit first for that. This is the limit as a approaches negative infinity. This is going to be, applying the fundamental theorem of calculus first, 1/2 times the natural log of, this would be 0 squared plus 2, plus 1, minus 1/2 times the natural log of a squared plus 1. So even though a would be getting smaller and smaller, so more and more and more negative, squaring it makes it positive anyway. And we can, we could certainly go and use values to determine this, but I'm going to graph this one again. And I just need to very quickly pop that into the graph here so we could see what is actually going on with this behavior. That way we can see what the value of it does indeed make when we apply that limit. In this case, as we go from negative infinity. But this is 1/2 times the natural log of x squared plus 1. You can probably see what's going on. before I even explain it. But if we're decreasing the value of a without bound, so the left-hand side here, if we keep decreasing it, this value increases, right? We're on 40 and we're, about 3.68. But this continuously increases, and it does not actually approach a specific number. As we keep going up, it keeps going up, which means this one sadly approaches positive infinity. But I didn't write the other integral yet for this, but since I have it up here, I might as well make note of it. That other integral, if we increase that one without bound, it makes the same phenomenon, where it's increasing without bound, not actually approaching a value, right? So this part here approaches infinity, right? And actually, since this one here was negative, I didn't put that negative inside of this. But if I do that, if I put that in here, it still doesn't give us an actual value, right? This will approach negative infinity, but not actually make any particular number. So doing this approached negative infinity, which means this one diverges. And we don't even really have to check the second one. Since one part of this diverges, that means the whole thing diverges. But if we did the second one, like I showed before, that one also diverged, which means this entire integral, both parts diverge. So just the negative infinity portion diverges, the positive infinity portion diverges, this entire integral itself is going to diverge. So let me know if you have any questions or concerns. Thank you.